Hello, this is David D. Hilster. I am a critical thinker, dissident scientist, and if you are not science woke, then this is the place for you. There are literally thousands and thousands of scientists from around the world who have been working for decades outside the mainstream, who have identified problems, fixed those problems, and who are proposing new theories and models. You won't find anything like this on YouTube, so you want to make sure you go down below and click on the subscribe button and the little bell next to it, and you'll be alerted to when our next video drops. Today, I love these days because I'm not just going and talking about the stupidity of mainstream physics and cosmology, but in fact, we have a brand new, hot off the press article that is a real paper, a scientific paper that can be found on dinox.org. I have a link down below, of course, and this is with our friend Stephen Hurrell. If you've never seen him, well, just go right up there. I have an interview with him, live interview that I recorded for my channel, but he has put out literally today. Today is, of course, when I'm recording this video is December 12th, 2018, and literally this is an incredible paper. I'm going to go through it in pretty good detail, but not all of it, but you can read it. Of course, there is a link below, and there's a link on this page, but I'm going to go through it, and I'm going to tell you why this is very revolutionary. Congratulations. My goodness, this guy keeps producing and producing. I am going to, hey, Stephen, I know you're going to watch this because I'm going to send you this video. And you're going to publish this in our proceedings for the 2019 CMPS proceedings. You have to. But anyways, what is the title? A paleogravity calculation based on the weight and mass estimates of a Brontosaurus bronchii. Boy, it chokes me up just to say it, but it's a giraffe titan, and it's like a titan giraffe. And so I bet when you see the picture, you'll probably understand what that means. But basically, it's paleogravity calculation based on the weight and mass estimates of this Brontosaurus. That is pretty amazing because we're going to get to it. Here's the abstract of the paper because it is a formal paper with references. This is publishable in our 2019 proceedings for the CMPS. But here is the abstract. There is great interest in calculating accurate values for Earth's paleogravity since the results have profound implications for many sciences. Boy, is that an understatement. One fundamental technique to quantify paleogravity is to compute weight against mass estimates of ancient animals. In this paper, the technique is applied to the Brontosaurus. I won't read that name, you can, but it's a Titan giraffe, I call it. One of the most complete sauropod dinosaur skeletons known, meaning they've got more than one and they're complete. The results indicate the paleogravity of 0.5 G 0.54 G, and that is a reliable estimate for 152 million years ago. So that's 152 million years ago. Gravity was at 0.54 G. Paleogravity, what does that mean? Gravity was less. And how they calculate it? They're using this big dinosaur. How do they do that? That's what this is about. This is really cool. And here is the actual paper. You can see published online 2018, 12th of December. That's today. I got it. Well, maybe it's tomorrow already in the UK. But anyways, there it is. I'm not going to read it again because that's the same thing. He just put it on his website for convenience. But now we're looking at the actual paper, which you can see below. We have a PDF link to it. Really cool. Introduction. Paleogravity is the study of ancient surface gravity on the Earth. You know what's so amazing? Can you imagine if we actually had a lot of paleontologists working on paleogravity? You know why they're not doing that? Because the physicists won't let them. Because they're going to say, what do you mean? The gravity's been the same. What are you talking about? Maybe a little difference because, you know, asteroids and all that. No, folks, this is why this is so wonderful. This is why you're watching this channel, because these kinds of papers, this kind of data, this is what if you have a new model of the universe, whether it's an ether model, a particle model, a lattice model, or a distant model, more traditional model, you need to take this into account. You have to take into account that the Earth and other bodies around the universe in the universe are expanding and they're gaining mass. So you're going to have to explain how that happens. Well, mass is mostly the nucleon, it's almost all the nucleon. That's where you get the mass of atoms. So they must be more atoms are in the earth, and there are explanations for that. So this is where truly physics and cosmology are today. All that other stuff, that's all flat earth stuff, that's all heliocentric stuff, earth-centric stuff. This is new science today. So there have been great interest in producing reliable estimates of paleogravity for at least half a century. In the early 1960s, Arthur Holmes and S. Warren Carey, two professors of geology, corresponded about possible methods of calculating paleogravity based on 50 different methods, eventually concluding that none could prove the accuracy needed to be useful. Over a decade, Carey, 1975, page 134, still reported that variation of gravity acceleration g at the surface has not been recognized, although no critical test has yet been proposed. So you can see right there, for those of you who don't know, Samuel Warren Carey is one of the modern fathers of the expansion tectonics, which was now passed on to James Maxwell. And he was saying basically, well, they're not really doing it and they don't want to do it because they don't believe that gravity has changed. So there's, he said, still reported variation of gravity acceleration at the surface has not been recognized. Has not been recognized. So that's what that means. But again, this is absolutely fast. Stewart, in all these years, studied various methods to estimate paleogravity. This is, boy, Stephen, I love it. I'm really reading this for the first time, believe it or not. I clip them out, I read them real quick, but then I read and really get to think about them with you, my subscribers. Although his methods were not accurate enough to estimate paleogravity to a high accuracy, he was able to set limits to variations in surface gravity. His general conclusion was that the studies undertaken indicated that the force of surface gravity had never been significantly greater than it was now, but may have been less. Okay, so again, because this is what makes this paper so revolutionary. Because what Stephen Hurrell is saying, that the people who are trying to do this really didn't have ways to calculate, and they just said, well, we're pretty sure it's been less, but we really have no way to even guarantee that happened. So you can see a number of authors, and all these authors, and you can see in there Scalera, he's an Italian guy. I know Maxlow is in there, you can see that. And there are many other people. Hurrell, there he is, Hurrell, Stephen Hurrell, 1994, 2000, yep, there he is. Have speculated that ancient life might indicate that paleogravity was less than the present average of 9.81 meters per second. Now it's really important that you note right there, or maybe we're gonna do this. We're gonna right there at 1g. 1g is gravity. It's what gravity. It's going to be our standard, which is gravity today. And remember what he said in the beginning. If you don't, stay tuned, and we'll see it again. Okay, let's keep going. The theory. It is well known that gravity can be quantified using accurate values of weight and mass. The weight of an object varies in direct relation to the gravity, but the mass of the mass of the same object never varies. Any mass would be approximately 1/3 its weight on Mars and only 1/6 on the Moon. Thus, any known mass can be used to calculate gravity. So that's what he's saying. If I know the mass of something, I can calculate gravity. An animal can be used to calculate gravity using the weight mass method, for its weight and mass are known if its weight and mass are known accurately. Okay, so if we know the weight of some animal, we can use calculated gravity. So an animal can be used to calculate gravity using this weight mass method. It naturally produces a gravity of 9.81 meters per second, or 1g. We'll just call it 1g. It's a lot easier for present day life on Earth. And here, paleogravity can be calculated by, well, GA is the gravity, the paleogravity of some predefined age. So G of some age, WA is the weight at that age, and the mass, and the M is the mass. So you can, if you know the weight at a certain age of a dinosaur, for instance, and the gravity at a certain age, at that same age, the constant, the gravity that's affecting the animal, then you can you get this equation. Since mass never varies, it does not need a subscript to denote its age. So its mass is its mass, it's its mass. The confusion about the large size of prehistoric life has, this is great, some history here. The confusion about large size prehistoric life has generated many different ad hoc hypotheses to account for the large size of sauropods, including specimens such as the the titan giraffe, the giraffe titan, Brontosaurus. That's really wild. He puts that every time in that's, I guess, the way they do it. What do I know? An early popular hypothesis, widely accepted for sauropod dinosaurs until the 1960s, proposed that they were slow lumbering animals that supported their bulk, massive bulk, by buoyancy, so they float around like big hippos in swamps. That's not what he says, but that's what I'm saying. Subsequent research indicated that these animals were land animals. Whoops! And the hypothesis was widely abandoned by the 1980s, although the problem of their large size still remained. But who cares, because, you know, drink the Kool-Aid. We don't care about truth. Just drink the Kool-Aid. Quick. The wide adoption of this early water-supported hypothesis means that mass estimates for sauropods produced before the 1970s are much larger than the present-day estimates. So what he's saying is you got to be careful of when they were doing it, because they had all these other assumptions around when they were trying to calculate these things. Beginning in the 1980s, it started to become popular to depict dinosaurs as very skinny animals compared to what were they? They on whole plant-based diets? Is that what it was? Or they were extremely agile and did a lot of exercise. Maybe they ran dinosaur marathons because very skinny compared to the present-day life. Partly because the large mass estimates of the land animals seemed incompatible with weight estimates calculated from the bone strength. These sleek versions were stripped of enormous soft tissue, reducing their mass estimate by a large amount. Some of these skinny reconstructions are still popular today. That's interesting. Oh, here's one. Right there, you can see there. Well, what is that? Well, that is a skeleton of a Brontosaurus, and this is the caption for that photo on his paper. Of course, this is in his paper, which came out today. Did I tell you it came out today? This is like cutting edge, bleeding edge. And of course, if you are science woke, you got to know this, because believe me, these are pretty much, the data supports this immensely, that the Earth had less gravity. And this is one of the papers showing it, and it's a breakthrough paper. I'll get to why. It was given a new scientific name in 2009, so the Brontosaurus became the Giraffatitan bronchi. It is the tallest mounted dinosaur skeleton in the world, standing 13 meters. 13 meters, you multiply that by, you get like, you know, what, 40 feet? Whoa! Was it 15? Wait a minute. Times 3. 3, that's a 9. No, I don't know. 3 times 13. What's 3 times 13? 39. 40. Yeah, I was right. Okay. As the Guinness Book confirms, the humerus, the upper leg bone, is taller than the average man at 2.31 meters long. This specimen is still an adolescent when it died. One isolated fibula on another specimen was 13% larger, indicating that it would have grown even bigger. Bone strength indicators. So they're talking about bone strength indicators, and that's one of the things that people who are looking, like Stephen Hurrell, the author of this paper, he is a mechanical engineer, so they're looking at the strength of the bone, what it's got to hold up, why does it hold up. If it's big, it's holding up, it's big for a reason. Three-dimensional computer models, they also try based on these things. So they're looking to try to construct these animals, these dinosaurs, as accurately as they could, to see if they can actually give them a weight. And here are the mass weight estimates for this specimen. And you can see from 1936 all the way to 2005, it varies from 70, 78, the mass, I don't know what this ton, metric tons for, okay, all weight estimates. So 78 tons, 40 tons, 31, 23. So it varies from the 20s to the 70s, maybe even 80. So there's a great variation. So makes a difference. So what are they going to say? Well, here's some of the ways they can reconstruct, and you can see that they're trying to put some flesh to the bone, sort of like people who are looking at bodies or just bones that they are, and they're going to try to reconstruct what a Neanderthal looked like from just his bones. So there, these things are in his paper about reading, the Brontosaurus model. This model scales from of 180. The estimated mass based on this model is 43 tons. And if you can look down here, the second one, the scaled mass is 60 some tons, or I think that's what it says. Sorry, it's really small. And then the other one down here is 56 tons, and this is a 3D. You can see these are like painted and calculated. Oh, this is like a 3D model somebody made out of, I don't know, plastic. This is a drawing, and this is a computer 3D CAD model. So they're trying to find as best they can what is the mass of this. Anderson team chose to study the major leg bone, which is often well preserved and otherwise incomplete fossils. A good indication of the weight of the present animal is the circumference of the upper leg bones, the humerus and the femur. The bones were measured where they were the thinnest, so the weakest, so the weakest, usually about halfway along the length of the bone. These two circumferences then added together to give a total circumference. So the Anderson team used statistical analysis to find the equation W, which is the weight body in kilograms, is equal to 0.000084. C is the total of the humerus and circumference in millimeters. So they can calculate the weight of the animal by this simple equation, and they're using statistical analysis, which means they had to have lots of data to do this. Not like neutrinos, where they have low-level data, which makes no sense. Just read Karazani, autodynamics.org. Read that. But so they have that. So they can plug this in. What does this mean? Why is this revolutionary? It's because when you look at this, you can plug in by taking a bone, the femur, or the the humerus and the femur, and you can take those, measure circumferences, and you can get the weight. That is truly amazing. That's what's revolutionary about this. And because of that, you can get paleogravity estimates. The bone dimension equation predicts that the legs of the Giraffa titan evolved to carry an animal that weighed 331.59 metric tons. Yet the volume method predicts the specimen's mass was 58 metric tons. Thus, the two methods can be compared to calculate gravity approximately 152 million years ago. So they've got the volume of it. They know what it weighs today. They are looking at the bones to say, this is what it weighed back 152 million years ago. So G of 152 million years ago, you can see that there. The G sub 152 equals the weight sub 152 over the mass. So what do we have? We have 31 metric tons over 58 metric tons of what the mass would be of this animal. So you have the mass, and then you have the actual weight of the animal, and you get 0.54 G. What does that mean? That means they have one of the first accurate paleogravity estimates and calculations, maybe the most accurate, well, probably the most accurate in the world. And we come up with what? Gravity was half of what it is today. So if you hit a golf ball 300 yards or 300 meters, it's going to go twice as far. If you can jump our basketball courts, everybody would be dunking. Gravity acceleration is calculated as 54% of our present surface gravity. So again, that's the G. So it's 5.3 meters per second in the gravity calculation, and it's 9.81 right now. So that is based on 152 million years ago. So, accuracy. In theory, paleogravity estimates using this weight mass technique should provide one of the best paleographic estimates possible. However, the accuracy of these results clearly depends on the precision of the weight and mass estimates. As previously discussed in Hurrell, that is the current author, 2012, typical variations would indicate that the results are only likely to be within the range of 15% even at the highest preserved specimens. Paleogravity estimates relies on producing accurate estimates of weight from bone dimensions and mass estimates based on the volume of accurate models. The diverse mass estimates produced by the number of studies clearly show many mass estimates for this animal are not constrained to a high level of accuracy. This is disappointing since the specimen is one of the most complete sauropod dinosaurs and the most heavily studied. Nonetheless, since the specimen is relatively well preserved, it can consider that the result be accurate in 20%. So even with the 20%, if we were to add it to it at 50, that's 70%. It would be 70% at the worst case that the Earth would have had 70% of the gravity it has today, which means it had less mass. And of course, if you looked into expansion tectonics, then you would, of course, understand that there are a lot of people, and the data really clearly shows that the Earth has been expanding for a long, long time, especially since about 220 or 30 million years ago, where it seemed like it was going pretty slow, and then all of a sudden there was a speed up and the cracking of the crust and the growing of the seafloor beds. If you want to see this in a few minutes time only, look up Neil Adams' Expanding Earth, and you will see it's been viewed millions of times. But this is an absolute revolutionary paper. Why? Because in my opinion, it's the beginning of paleogravity, a modern new look at paleogravity. This is where paleontologists should be working. This is where anybody who is science woke, you should know this, because if you are looking at certain theories, or you subscribe to somebody's theory, or you are looking even to try to come up with a model of the universe that's better, you got to take this into account. You got to take into account that the Earth has been expanding. Data shows that, and not only that, it's been gaining mass. And that, of course, with the dinosaurs, and that's all what Stephen Hurrell is all about. And he is about, if you haven't read his book, it's on my list of must-reads, Dinosaur and the Expanding Earth. But this is, take a look at it. The link is down below. I give my absolute applause. This is why this channel is different, because some of my subscribers says, David, it's really cool because not only you just complain about modern physics and tell us where it's really stupid, and I'm getting that part, but you tell us where it's at now. And this is absolutely fantastic. And remember what I say, don't take my word for it. Stay critical, stay thinking. I am David D. Hilser. I am your science therapist trying to get you science woke. Ciao for now. Woohoo!